you to the organizers for inviting me, having me over. It's a great conference. I enjoyed it. I learned a lot of new things. And I apologize straight away because Sharina in her plenary talk today stole half my presentation. So lots of these things you will hear now, you've heard before already. Anyway, I think these points are important enough to mention them twice. So the work I will show mostly, as far as I show something, has been done in collaboration with David Daschbill and Craig Roberts and affiliated students. So, why quark matter? And you've seen that, so I start one-to-one in similarity. So why is it interesting to investigate whether there's quark matter in compact stars? And a natural answer for that is really to look at the phase diagram of QCD as we imagined it. So here's the temperature axis, here is the density axis, and down here in that region we expect that neutron stars live. It's not quite clear whether it's here or it extends into that phase. But there are a lot of things which are not clear neither about this diagram. So it's often shown, but actually it's a bit misleading because there are many things which are not really clear. So what's so complicated about quark matter and neutron stars is that it's a completely different regime compared to that where lattice QCD works as an exact solution of QCD. So lattice QCD is here at finite temperatures, maybe small chemical potentials, but it really doesn't go over the critical point. If it comes close to it, we are lucky. And it certainly fails here at the low temperature regime because the fermion sign problem is there and lots of complications. So there are some approaches how to solve it, but really none of them looks so promising so far. On the other side, of course, we see that these are two axes of the phase diagram, and heavy ion collisions are somewhere in between, so it would really be nice to check our understanding of matter as it works as a theoretical concept, but it's consistent from here to there. So that the whole thing is a bit more complicated. You see if you look at the phase diagram, which has been stolen from GSI and significantly extended, so that here you find in Lubna, where Nika is planned. So this project here, where we want to probe the rather low temperature branch. There you see that compact stars actually are a bit more complicated than that they're just on that low regime, but they have that high asymmetry, which makes it really distinctly different from what we know from heavy ion collisions. The other thing is that there are lots of hypothetical regimes. So quark-ionic phase is one example where you have chirally broken, or you have a restoration of chiral symmetry, but still confined quark matter. That's the idea of quark-ionic phase, which is just an idea. It has to be proven or not, but there's something like that. There are other questions, for instance, about the critical line. So some people doubt that you would be able to observe something like that. Some people doubt that the critical line really goes down to 0 temperature. So it could be that the critical line goes from here to there. There are lots of different theoretical scenarios about how the QCD phase diagram has to look like. And certainly compact stars which are living in this region are a good tool to probe the ideas. So quark matter is what might be inside a neutron star. We don't know about that. So there are basically 3 scenarios at the moment how a neutron star would look like. It could be just the neutron star as we know it. There could be something like an inner core which consists, for instance, of quarks, but it could be any exotic kind of matter. So hyperons have been mentioned today excessively. And then there's a third scenario where we really have a pure, strange quark matter core with just a crust on it, but this one I leave out. So what the aim of my work is really to single out, to find a smoking gun, whether this is the case here or not. So smoking gun. Of course, there's an alternative to that. The alternative is that quark matter in neutron stars is just a very nice idea, but we have nothing in our hands to prove it. No smoking gun at all. Might be. At the moment, we can't prove it and we can't disprove it. That's a good situation, that's a bad situation. It's a bad situation because we can check our theories. It's a good situation because we can come up with lots of theories about how we imagine things. I will come to the picture a bit later to explain you or to give an illustration for how inventive theories can become. Or maybe back to the picture here again. So if you let children play, there's one thing which you always have to keep in mind. They need rules. So without rules, playing is pretty fast hurtful. So our rules are constraints. That's what we put, and that's what we roughly know about neutron stars in this case. We know that the masses are somehow in that region. We have a fair idea about the radii, even it's not very good. We know a bit about the temperature H distribution. We know redshifts, rotation, and the breaking of the rotation, of course, is useful information. The optimum would be to have all this data available for as many neutron stars as possible. In particular, it's important to have all this information available for single neutron stars. One neutron star, all that information, that really would give us something. Not everything, but something. The reality of, however, is that we have some of this data for some neutron stars, and not all of them are undoubted. And still, that's what I want to illustrate in the following, is that we can learn something about matter at supersaturation densities. Two data which I think are crucial is that often mentioned now measurement of two solar mass neutron stars. The accuracy is remarkable, and it's remarkable too that at least about the Deimos pulsar here, there is no significant disagreement as far as I noticed in the scientific community. So this seems to be a solid measurement. It's purely relativistic. There are model assumptions in it further beyond that. Here I hear some slight doubts, but it's not so bad. The other one, which has been mentioned this morning the first time during the whole conference, which I think is very important too, is the rapid cooling of Klähn. So even though it leaves some room for interpretation how it comes, it's a very crucial data. Why is it crucial? It's crucial because the situation so far was this. So we have the temperature, we have the age, but we don't have the time evolution of the temperature. And this is what has been measured for Klähn. So that would be the typical plot, as we know, temperature, age, but here you see there have been a number of measurements within 10 years which really give us information how the temperature develops over time, and that is crucial to understand the interior of a neutron star. So why are two solar masses so exciting? And that's not just for quark matter, that's in general the true thing for everybody who's interested in the equation of state of dense matter. Speaking about nuclear matter, far beyond saturation density, it's not well understood. So this is actually a quite old slide, I use it all the time, but it's still true. If you do such a Bethe-Weizsäcker kind expansion of the energy per particle as a function of density and asymmetry in the system, then you can look what the leading orders are next to leading orders here in the symmetric part of the equation of state, here it's in the asymmetric part, so the contribution due to the asymmetry of the system. Then you will notice that for the compressibility, so here this curvature in the saturation density, there's some agreement. I wouldn't say it's agreement, but okay, we roughly know the number. If you look to the next order, and this is what often leads to confusion, if you speak about stiffness and softness, why the compressibility is not a good number to describe an equation of state. Here we have a disagreement, not about the number by itself, but about the sign of it. So we don't know how stiff or soft it gets. The same we have here in that asymmetry contribution. So J is rather well known, L, there's a difference of a factor of 2, about. Then again, why is it interesting to have a two solar mass neutron star? If you take all the equations of state I've shown on the slide before, and you plot the mass as a function of the density, and then you plot the energy of the symmetric system, the energy per particle of the symmetric system, it has nothing to do with the neutron star yet, as a function of the density, then you will notice that this correlates. So the stiffer, and here stiffness really means how far up I get at significant densities with the equation of state. The higher I get up here, the higher I get up with the mass of the neutron star. So here, stiff, higher, maximum masses at smaller densities, soft, smaller masses at higher densities. You will notice, or actually you can't notice it here, but one can show that the compressibility, which gives the stiffness in this small area, really is not the crucial number. So why is that interesting now? Because this is just the contribution to the symmetric equation of state. This is actually an indirect link between neutron stars and heavy ion collisions, because that's what we have in heavy ion collisions, roughly symmetric matter. And that makes sense somehow, because the systems, if you look at heavy ion collisions, are roughly the same. Of course, this is a bit I made it to look good. But here, that's the argument which Gina gave this morning too already. So the size of the system is different, the number of particles is different, but if you look at the densities, they are roughly the same. 4 times saturation densities, it's something you can reach in a collision, up to 9 times saturation density in a neutron star. Actually, it's probably below that. Constituents are roughly the same. There, Gina made the arguments about what's not the same. Yep. So then again, that has been shown this morning too. That's the analysis of the flow constraint by Danielewicz. What you can extract from that is a relation between the pressure as a function of the density. You get such an area here. Actually, the original area was this. This here was an extrapolation we did in 2006. So there's an upper bound to the pressure, and there's a lower bound. And in a first estimate, you can say, okay, every equation of state we have, if you take the symmetry case, should be somewhere within that region. That's how we understand it at the moment. If we do that with the equations of state I've shown before, and you see some are too stiff for that, and most of them are very, they have actually no trouble to explain that. Here's an interesting observation I want to show because I find it very interesting. If you just take this upper bound here, construct an equation of state from that by just drawing it, add some asymmetry to it due to the asymmetry, so since we want to go to neutron matter, and you calculate neutron stars from it. Along that upper boundary, you end up with a maximum mass of about 2.1 solar masses. That's just going along the upper line. It's not an estimate of what the actual upper mass could be because you have different trajectories through that region. But this is what heavy ion collisions show if you take them in a very naive way. What you see on the other side is that the lower bound here comes up with masses which are not in agreement at all with what we know. So here's a situation where heavy ion collisions could constrain the neutron star equation of state, and vice versa. And that is illustrated here. What we actually know from both of these constraints is, if you take all these equations of state, some of them are not stiff enough to describe these high mass neutron stars. They are not heavy enough. These are not heavy enough, and that's because the equation of state is not stiff enough. The flow constraint wouldn't have any trouble to live with these equations of state. However, there are some equations of state which have no trouble at all to describe these high masses. However, here the flow constraint says it's too stiff. So that's really a link between heavy ion collisions and neutron stars which I like and which needs to be elaborated over the next years. And in particular, the flow constraint, most likely not by me, but whoever wants to look into that, it would be really welcome. So, what does it say about quark matter in neutron stars? Can quark matter be present in massive neutron stars? I said that a lot of times, and I do that on purpose. Presently, one cannot know. You will hear other statements where people say, ah, it's ruled out by whatever. It's not what it is. It can be there. However, if there is no quark matter, and we can prove that, it's likely that it's no other neutron star we know. That's actually quite simple, because if you want to have a higher maximum mass, you need a higher central density. That means if you don't have it at high central densities, you can't have it at low ones. Okay. So, quarks, of course, are there. The question really is how we get from here to there. And that is a problem already. It's a problem because our microscopical understanding of QCD or our methods of solving QCD are not sophisticated enough to do that. We can't describe a hadron in dense matter in terms of QCD strictly. We have to do something about it. And this is what the reality is at the moment. What we do is we model a nuclear equation of state, we model a quark matter equation of state. Both models don't have necessarily anything to do with each other. Actually, they don't. These are usually two different approaches, and what we do is we perform a phase transition construction, and that's sketched here. So here you have the pressure as a function of the chemical potential. You say at a certain, then you compare both equations of state. So the red one here, that would be the nuclear, the dashed line, that would be the quark matter equation of state. And then you just look, okay, where I get from one minimum of the canonical potential, of the thermodynamical potential into the other, which means where I have the higher pressure. If the pressure switches, I go from one system to the other. That would be the classical Maxwell construction. You see that behavior here. So since the slope of the pressure changes and the derivative of the pressure with the chemical potential just gives density, you will have here a density jump in that point, and that's what's shown. This is typical density jump in equation of state. Pressure as a function of the density would look like that. So this plateau is a typical thing. What Alford has shown in 2004 already is that actually that slope doesn't have to be very different. It can be almost the same. And then you run into that situation. If the slope is almost the same, this density jump becomes very small, which leads to that the resulting equation of state looks very similar to that what you originally had to the nuclear equation of state. One can use the information either from neutron stars or from heavy ion collisions from every side you want to adjust the Quark equation of state, to constrain it in this point where they are not clear. I do that here with an NGL type model. It's really one out of many. There is a manifold of them, and this one is characterized by an interaction part where we have the scalar interaction. This one is important to acquire mass for the quarks. There is a vector interaction. That vector interaction basically renormalizes the chemical potential, which leads to the stiffening of the equation of state. And we have diquarks, which have some effect on the position of the whole curve. We need that in order to play a bit around. I will show that later. From that, you can calculate the thermodynamic potential. What you get basically is a free Fermi gas. It's just particular in a few points. You have the occurrence of these gaps, and you have modified dispersion relations. So your theory looks like a free Fermi gas, but actually it's not, because the masses become dependent on the chemical potential, as do the chemical potentials, which are effective potentials there. What you can do now is you can take that model, calculate the Quark equation of state, make the phase transition, and construct something which goes along that line of the phase of the flow constraints. That's what we did here. So these are different parameterization, and you see that you can play nicely with where the phase transition should occur, how stiff or soft the equation of state is, and then you can see whether that is in agreement with what we know about the mass and the radius of a neutron, or in this case a hybrid star. What one sees is that one can actually fix some peculiar behavior. So this is the DVHF equation of state as we know it. It has trouble with the flow constraint. It's a bit too stiff at very high densities. We can soften that down with the transition to quark matter, and this is what happens here, and we would still be fine with the mass-radius relationship. And that's scary now, yeah? So what we did here was to vary these two parameters. So eta v, as you see, relates to the stiffness of the equation of state. A small value here gives you a rather soft equation of state. A large value gives you a stiff equation of state, which means you have high masses. We did a more systematic study of that. So it's the same parameter here. This gives you the stiff equations of state. However, the diquark coupling here plays a role too. So if you alter that, you can get stiff or less stiff equations of state. We did that study in order to locate points in that parameter space of couplings where you can actually find reasonable solutions which would predict massive quark force. So, and that would be here, which is actually interesting because that value of 0.5 is one which one would obtain by just the classical Fields transformation arguments. However, that diquark coupling has to be pretty large in order to be in fulfillment of that. So this here describes any parameterization which obtains the mass for the hybrid neutron star of 1.97, so roughly 2 solar masses. These black lines you see here indicate what mass you have on the transition from a pure neutron star to a hybrid star. So that means here you have a star which has a maximum mass of roughly 2 solar masses, but you could expect, for instance, along that line that it would have a quark core starting from 1.5 solar masses. So that means here you have the really massive solutions. If you go too far up into that direction, then you would obtain pure quark stars, but that actually is rather a pathology of the NGL model. If you go too far this direction, the transition happens too late, and you wouldn't get a hybrid solution anyway, neither. What you can do then is you can look for the onset of quark matter in symmetric matter. So not for neutron star matter, but for symmetric matter. And you see that there is some correlation as well. So if you find that very massive objects, you automatically realize that the transition has to happen not below a certain density here. In that case, I would say roughly 4 times saturation density, which is interesting too. So that's an indirect information for the guys who are actually running that heavy ion collisions where to look for it. So it's quite remarkable. You can rule out quark matter in neutron stars. Even if you rule it out, even if you say there is none, which would be this case here, this upper line, it would be helpful for heavy ion collisions, because then you know that the transition density probably is even beyond Z4. It's rather 4.5 or 5 times saturation density. So it's indirect. It's a bit. It's not obvious, but it's nice. A disturbing twist I wanted to report, and not to support, I want to report. The underlying assumption for performing a phase transition is that we actually fairly know the equation of state of both nuclear matter and quark matter. That of course is not the case, and that gives you some freedom in your interpretation of what you can do for phase transition. So if our models break down, then it's very likely that they break down near the transition point. There's a recent paper where these 3 Japanese colleagues used the freedom. And what they did was that they say, okay, we don't know the equation of state in the transition region, therefore an interpolation between the region where the nuclear model breaks down and the region where the quark matter model breaks down, we can just interpolate. So it's not the classical phase transition anymore, we just interpolate. So they had 2 methods how they could do it. One was that they interpolated the pressure as a function of density. As it turned out, this here is thermodynamically inconsistent. However, if they do the same stuff in epsilon over n, so the energy density per particle over n, everything is fine. So you see, they say somewhere here, nuclear model breaks down, somewhere there, we know roughly what the quark matter equation of state looks like. Actually, they don't know it, they just guess it. Then they interpolate, and now comes the twist. They interpolate from a soft equation of state to a stiff equation of state, and that has severe consequences. If you look into the pressure as a function of energy density as a result from this, there's a significant stiffening of the whole story. That means, for instance, that the speed of sound in the system would increase terribly, so it would go close to the speed of light, and that's in contradiction to what we expect from a regular phase transition, where it actually would have to drop. So it's a complete opposite behavior. It's getting worse, or better, depends on what you want. In a classical phase transition, it's always like that. You have your nuclear equation of state, you have your quark equation of state. So this here would be the nuclear, very stiff, gives you a high mass. You have some quark matter equation of state, could be one of these, or actually rather goes here, which is rather soft. You make a phase transition, you get a hybrid, which is somewhere in between. So that's the situation. In the clueless interpolation, as I'd call it, because you say, okay, I don't know where it is, I just guess something, you end up with a complete opposite behavior, if you want to. You have a very soft nuclear equation of state. The quark matter equation of state, they didn't show in the plot, but it's somewhere below the 2 solar masses as well, at least for this coupling here, because it's 0 vector coupling. It's impossible within an energy model to describe 2 solar mass neutron stars. But you end up with a very massive neutron star. So you easily get it up to 2, 2.5, probably you can go up to 3, it depends on how you interpolate. The way they interpolate is not fixed, there's no rule for how to do it, you can do it in whatever way you want to, and you end up with something like that. Why I'm showing that? Because, again, if we allow something like that, so if you say, okay, we give up on exploring the transition region between nuclear and quark matter, and we give ourselves this freedom, that basically means that we are at the end of an approach for a microscopic description, because with this construction you literally can obtain whatever you want to. No rules anymore. It's playing without any further rules, and usually that ends up in tears. So short conclusions. Actually, I will quit that because I don't know how much time I have left.
Oh, you still have 10 minutes?
10 minutes, yeah. I quit that. Quark matter. So what I'm proposing here is to say that instead of living with that situation forever, that we have to somehow interpolate with one phase and the other, and to take different models, why not try to put it together? What's the problem about quarks? What's so complicated? There are two things which are complicated. So the most complicated thing is here in the beginning, it's confinement. We actually don't understand confinement really well. We have a very naive understanding of confinement. Confinement for us means there are no free quarks in the world as we know it, and that's roughly it. What we don't really have is a formal requirement for what confinement is. If you ask specialists on the topic, they will come with probably 3, 4, or 5 different answers how to describe confinement. However, they are confined, and they are confined in baryons and mesons, and we want to describe the transition between one and the other, and we have to understand confinement. Another thing which is particular for quark matter as well, that's the dynamic generation of mass. That probably is known to everybody. So the proton has roughly GeV mass. However, the constituent quark mass is each roughly 5 MeV. So that means that 98.4 something % comes from somewhere. If you look at a 3-particle system, so 3-quark system, which would be a proton, and you divide it, so actually we have 313 MeV. If you look at a pi and 140 divided by 2, we have 70. It says so, it's not simply just adding up, there's some interaction involved, and that interaction happens obviously in a very non-trivial way. So quark mass is generated by interactions only out of nothing. Actually, in a good model, if you put here 0 MeV, you would still obtain roughly 1 GeV. That's why Higgs, for instance, for us is not so important. We actually don't need it, we can live without it, but of course it's nice to have it. So where does it come from? Of course, we know the answer to that question. The interaction in QCD comes through the interaction of gluons between the quarks, and to make it worse, gluons are interacting with themselves, and that in the end leads to the breaking of chiral symmetry, which is reflected in the gaining of mass. It's a distinct, non-perturbative feature. Any perturbative approach who tries to describe that will fail. Confinement and the breaking of chiral symmetry are related to each other. We don't know how exactly, but it can be shown in lots of studies that there is a connection. If you have a breaking of chiral symmetry, then accompanied, it is accompanied, there are good indications for that, it is accompanied by confinement or deconfinement, depending which way you go. So what we need in order to investigate the quark-hadron phase transition is a non-perturbative approach. What do we have at the presently? One is the back model. Back model basically is an ideal gas of quarks. You add some pressure to the system in order to describe the back that confines it. So in that sense, you have a natural confinement in it. However, it does not exhibit the breaking of chiral symmetry. Quark masses are fixed. NGL models are the opposite somehow. So they account for chiral symmetry breaking, so they can attain mass. They are applied exactly because they do that. It was an experience from nuclear models actually that they work this way. However, you won't find confinement in these models trivially. So there are some modifications for NGL, and probably I should mention now the quark meson model too. So it isn't accounted for. However, it holds it's inspired by, but in no case based on QCD. Lattice QCD doesn't work neither. It still fails at T0 and finite mu, or at least at significant finite mu. And what I want to propose and what I want to investigate for the next time is the Dyson-Schwinger approach. So what is the Dyson-Schwinger approach? You derive gap equations directly from the QCD action. What you obtain are the Dyson-Schwinger equations. You have to be a bit careful, of course, there too. You can complain that it's not necessarily diverging set of equations. However, I think it's the best thing we have at the moment. It works successfully in the vacuum. It works successfully at finite temperatures. I see no reason to not do it at finite chemical potentials. So one example for how successful it works is this plot. This is the momentum-dependent mass, the dressed quark mass as a function, of course, momentum-dependent, of the momentum. That's something we don't have, neither in NGL models, nor do we have it in a back model. So the momentum dependence is something which is already related to confinement. You can argue about that, but if you can describe confinement, it certainly comes from momentum dependence, or it's reflected by the momentum dependence of the quark. So these solid curves here, they have been calculated in the Dyson-Schwinger approach. These dots here, this is lattice data. The remarkable thing about that is that the solid curves are older than the dots. So here the Dyson-Schwinger approach was faster than lattice QCD, and it was pretty correct. It has some other advantages. You can describe bound states, so starting from diquarks or mesons or whatever you want to, then you can go up, try to solve Faddeev equations or some simplified Faddeev equations, where you exactly solve in the spirit of what Julina spoke about today, that you speak about quark meson or quark diquark couplings. This would give you hadrons in the end, so this is possible. It has been done in vacuum. There's no problem. There are lots of problems with that, but it's possible. So why not extend it into the medium? It's barely explored in the medium. Okay, this is a bit messed up. A natural point to start with is the one particle description, and that would be an example for that. So what do we have? We have here the typical propagator, or inverse propagator actually. Here we have the free particle contribution to that, and the self-energy. The self-energy itself now depends again on the propagator. You have here a Quark-gluon vertex, you have a gluon propagator. It's a typical self-energy structure, and as you see, that thing has to be solved somehow self-consistently. That's possible very well. So where does the medium enter? Actually, it's quite simple. What it does, it adds an additional term here, at least if you're in a Klähn metric, which we do. So, however, that brings you some trouble too, because this revokes Poincare covariance. It means that it makes your problem much more difficult. So it's a challenge, but not a surprise, and nothing you can't handle. So the general solution of that equation looks like that. So you have here some scalar gap, which is the mass, roughly. And you have another term which gives you a modification of this part, which usually would give you the free fermion behavior. However, this is medium momentum dependent. If you do that whole thing in medium, it's just getting more complicated. So this one here is degenerated. This is degenerated. Yeah, this is degenerated. So you have two solutions. Suddenly it breaks up, one into time-like direction of the momentum, this is the space-like direction. The gaps have a more complicated dependence on the exactly same directions of momentum. Of course, it depends on the chemical potential as well, which holds for the scalar solution too. So you have one more gaps. Gaps are complex valued, and they depend on form momentum, energy, and chemical potential. Solve this, and you get the equation of state from thermodynamics. At least that's the plan. How much time? 5? I'm very good. There are lots of problems. Of course, you have similar equations for the gluon too, which you would have to solve self-consistently too. And of course, one has to do that, but maybe it's not the best thing to start with, because if we want to make progress, we have to start somewhere, and maybe in a careful way. So the way how you solve it now is that you say, okay, about the gluon, actually, I don't know so much. I know a bit. I can just take here the free gluon propagator, and then I specify the behavior of the coupling here. So I just put all that stuff I don't know into this part. I made another approximation for the Quark-gluon vertex, which is very simple too, and I end up in something which is called rainbow approximation. That behavior here, there's an ansatz which works very well in the vacuum. It has different contributions, so there's an infrared strength here, one with 0 width, one with finite width contribution, and here is running coupling. This is actually what reproduces you lots of the results you would expect from QCD. This here results rather in Toyn-Rules. If you take it all together, you have a fair description, at least of the vacuum. How it will look in medium, we don't know. If you take just one or the other term, you end up with two already published results. One that's simple here is in particular very nice and handy because you can solve it analytically. That's what I did a while ago. If you take the second term, you can't solve it analytically anymore, so then it's really numerics. This is what we did together with that colleague Chen here, which later actually made an equation of state for that. So there exists at least one equation of state obtained in that framework, which seems to work fairly well if you do the proper, fairly well, not perfect. There's lots of work to do. Interesting point is you obtain an NGL model in this framework if you take a delta function in configuration space. So it's all in there. So what would one expect from that toy model here is just a delta function. It's interesting already. So here I look at the one particle distribution function, which usually we describe just as the Fermi function, distribution function. That's what you would have for, you know it all. Okay. What you usually would expect is that you have something like a Fermi edge. Yeah? If you have chemical potential, okay, this one goes like 1 up to the chemical potential, then it drops down. It's not like that in this model, not at all. There is no Fermi edge behavior up to very high chemical potential. So here I increase the chemical potential, and you see this is not nearly 1 for 0.2 GeV, 0.4, 0.6, 0.8, 1. The chemical potential has to increase a lot before we approach what we know as a free particle behavior. It's 10 GeV here in that picture where I scales the momentum over the chemical potential. You have to go extremely high in order to obtain that. It's a toy model though. It has consequences. One of the consequences is that if you look at the pressure and you compare it to the back model or the free Fermi gas, then you see that there's a distinct different behavior. It's a mu to the 5 dependence instead of the mu to the 4 dependence, which we would expect. Since I probably have only 2 minutes left, let's go to the next one. That's the other model, which is a bit more sophisticated. It's not as distinct as in the toy model we had before, but still the fact is the same. You don't reach that 1, so you will never have the full the Fermi sphere fully inhabited. There's something missing. So that two things are, I think, are motivation enough already to go on with that studies, because Fermi functions really are important for all properties which are related somehow to dynamical processes. Luminosities, for instance, they play a role. And that would be the conclusions, which I skipped, so I will show them in the end, because I wanted to advertise. Please write down the link here, what you can get there are lots of equations of state. It will be more in the future. We are just collaborating to put all that stuff together. ComStar online supernova equations of state. We provide equations of state, as many as we can. Right now we have a number of supernova equations of state. We developed, I don't want to read it. Just go there, look at it, because I think it might be useful for everybody who needs equations of state or who provides them. And that is sponsored by lots of agencies, which I want to mention too. And then I come to my conclusions. I can make it very short. There's much stuff that has to be done, and I think it should be done, and I will contribute, and I would be happy if other people do too, and try to get away from the phenomenologic approaches and try to finally do microscopic physics in that domain, because it's worth it. Thank you.